Alright, so we're going to talk about a fairly counterintuitive problem, and that has to do with milk in a conical flask. Not something I don't know if I've ever thought about it before, but here we go. So basically the question is, we put some I guess non-homogenized milk in a conical flask like this, and then we're going to let the cream rise to the top. Okay, the volume of the milk is going to stay constant, but it's going to separate into two layers, like this situation. Not sure how well the two colors are showing, but this color up here is lighter, this color is darker, indicating a larger density down here and less density up here. Okay, all right. So we're going to go from this situation of a sort of a mixture of these two liquids to where they separate out based on density. All right. And our question is, what happens to the pressure at the bottom of the flask? All right. First of all, conical flasks and the shape of this flask is actually really critical to this problem, because you think, well, just for example, let me draw a different situation. Suppose we had just a beaker, right? So just a straight up cylinder here, and we're going to fill this one up also with milk or whatever, a fluid of the same density, right? We fill it up to the same level. Well, the pressure at the bottom is going to be the same, all right? Because the pressure is, the force divided by the area. Basically, it goes, if we have just a height h that we're filling these up to, then we have basically the force, right, is equal to mg, right? It's just the weight of the fluid, and the mass is the density multiplied by the area multiplied by h, right? So here's the density multiplied by the volume, A times h. All right, so that's the mass, and multiplied by g. Okay, so when we go for pressure, which is equal to force per area, then we just divide this A over here, and we get the density, the height h, and g. So because these are filled to the same height, they have the same pressure. And at first you think, oh, well, if I had drawn these more, where the bases are, they have the same cross section at the base, right? If this one were over here were as big as this one, you think that's a little strange, because obviously this holds less liquid. If you had these at the same size, and this one gets narrower at the top and this one stays wide all the way up, this one would obviously hold more. And if the force here at the bottom is equal to pressure multiplied by the area, and they have the same pressure, there should be the same force on the bottom, and they should weigh the same when you put them on a scale. But that's not true. And the reason it's not true is if we look at, say, a point right here, pressure at this point is exerted in all directions. So that means there is also, well, if we divide it up this way, there's an outward component and an upward component, as well as, a downward and inward. All right, so it's exerting force outward on this flask, so the flask has pressure out this way, which this cylinder does too. But because of this angle of the side of the glass here, we also have a component pointing upward. All right, and so when you look at the force pushing downward on this whole flask, you also have to take into account the force pushing upward on these sides. And obviously, you know, you'll have to take out this little area for the opening where there's nothing for this. There's no part of the glass for the fluid to push on, right? Okay, so that's just, that has to do with this problem, because we have a fairly counterintuitive result when we actually look at the cream separating from the rest of the milk. All right, jumping straight to that result, the pressure decreases at the bottom. All right, as the cream separates. Okay, pressure at the bottom decreases. All right, so this is at first, you know, if you're you know, at first it's counterintuitive, because maybe you're thinking, you know, the pressure multiplied by the bottom here should be the weight of the flask. If the pressure down here is decreasing, then the flask full of milk should be getting lighter as it separates, which obviously isn't the case with, you know, conservation of mass and all these different things. You know, this is true even if you put a cork in the top. There's no evaporation, yada, yada, yada. We just also have to remember that if the pressure down here is decreasing, the force pushing upward on the flask is also decreasing. So if they both decrease, then the total force downward on the flask can remain constant, so the weight of the flask remains constant. All right, so let's talk real quick about why this is. If we look at the pressure down here at the bottom, all right, I'll just call that P. All right, and we look at our equation for pressure, rho H G. We have the rho of the denser milk down here, and let's call this H1 maybe, I don't know, and then up here we'll call this H2. All right, so if you can't tell, right, this and this, these are the levels of the line between them and then the top. All right, so we have rho H1 for the milk down here, all right, times G. All right, so that's the pressure from this portion, okay, and then we are going to add to that the rho H2 G of the cream on top. And I guess really I ought to put little subscripts on my rows as well. They're in different colors, but that doesn't count for much. Okay, so we're adding these two pressures together to get the final pressure here at the bottom. And the real key to this is the conical shape. When you have a volume of cream and it's all mixed in here, you know, that's just that. But when you bring all the lighter, you know, the less dense cream up here to the top, the volume of the cream stays the same, but as you move upwards in this flask, the area is decreasing, all right? So since the volume's the same and the area is decreasing as we move up, as the cream is moving up, right, the area is constrained and the height, right, this I guess this H2 minus H1, or just looking at this height right here, this height is going to be larger, okay, then say if the cream all sank to the bottom, it spreads out over this wide area and you just get a small height. The pressure only depends on the height, not this area, right? So as we bring the liquid of lower density to the top, we are giving it more height. If that's a kind of an awkward way to say it, but that just means that this term here is weighted more heavily because the height is larger. Suppose we were to invert this flask, right? Suppose, we could imagine a weird, I'll draw a tiny, okay, this one's really weird, but we have maybe a little base, and we have a weird flask like this, right? That's maybe like a perfume bottle or something, I don't know. And then say we had our, our layers of fluid here, right? This would be the opposite situation, And this as something moves to the top, the height of its layer, the width of its layer decreases, all right? And, okay, let me just, I guess I need to really quick be clear here. When I mean H2, the way I wrote this, I'm referring to H2 is the difference here, okay? If this is just a coordinate, I guess what I would put here for H2 is an H2 minus H1. But the way I wrote it, the H2 is that difference, okay? Anyway, so yeah. So with a flask like this, we are giving more weight via, how much height each component of the fluid has. We're giving more weight to the things on top. They have more height, and therefore, because they have the lower density, we're counting the lower density more and the higher density less. And so that's why the pressure decreases.